Hi, I've already introduced an economic example for panel data. Specifically, we looked at the causal effect of a tax on alcohol consumption of the number of road fatalities. In this video, I want to look at an actual real data set for this example, and I want to implement the first difference transformation in Stata. Here I've already opened the data set, and it contains 4 variables: state, that gives us the state identifier, year, then the beer tax in dollars, and the fatality rate. So for example, the first row gives us data for Alabama in 1982, and the second row again gives us data for Alabama, but this time for 1988. For every US state or every unit in our panel data set, we will see 2 rows, because that's how many time periods we observe. This is the standard representation of panel data, and it's called the long shape of panel data. We can rearrange the data so that every row corresponds to one cross-sectional observation. Right now, for each cross-sectional observation, we have 2 rows. Now I've changed the shape of the data. Now you see for every US state we observe a single row, and in this row we store the information for both years. For example, now we have a variable tax 1982 and a variable tax 1988. I like this shape for panel data because it clearly shows you that panel data is just some special kind of cross-sectional data. Indeed, as we do for all cross-sectional data, we have 1 row for each cross-sectional observation. Let's start by pretending that we only have data for 1982, and let's do a scatter plot of the fatality rate versus the tax. And what we see is this: so the beer tax here is on the x-axis, the fatality rate is on the y-axis. Every point here represents a US state in 1982. It's not clear that there's a relationship, not easy to see. Maybe let's add a regression line. And we see that if anything, there's a positive relationship. What do I mean by positive relationship? Well, this red line here is from a simple regression, so the slope here basically gives a correlation. So that this line is upward sloping means that there's a positive correlation between beer tax and fatality rate. So states that have an above average beer tax also tend to have an above average fatality rate. That's what it means. We understand that correlation does not imply causation. At least that's one of the more important messages that I want you to take away from this course. And it could be that there is no causal effect of a beer tax on fatalities, and that instead we see the positive correlation because states that are more likely to implement a beer tax also just have intrinsically higher road fatalities. In our panel setting, we can model the total effect of all state characteristics that don't change over time by a fixed effect. It is perfectly possible that this beer tax does not have a causal impact on the fatalities, and that instead the beer tax is positively correlated with state fixed effects, and that this is what is driving this upward sloping line. Or in other words, it's perfectly possible that the beer tax has no causal effect, but still we are estimating a positive effect, and that is because of OV bias, because we are omitting the state fixed effect. In our panel setting, we can solve this OV bias problem by using the first difference transformation to eliminate the fixed effect. Let's do this for this example. So instead of looking at the absolute values of the tax or the fatality rate, we are looking at changes over time. For example, we're going to look at the change of the tax from 1982 to 1988. So let's generate a new variable. Let's call it D tax for tax difference, and that takes the 1988 tax and subtracts the 1982 tax. So this is the change from 82 to 88. Let's execute this line, and you'll see we have a new variable showing up. And for example, for Alabama, it's a small negative number because for Alabama, the tax decreased slightly from 1982 to 1988. Let's define a similar variable for the change in the fatality rate. And then let's plot the tax change versus the fatality rate change. So you see on the x-axis we have the tax change, on the y-axis we have the change in the fatality rate, and every dot here represents a US state. So as a state, if you didn't change your tax, it would be on this vertical line. All the states here in the positive range increase the taxes on beer, and all the states here decrease the taxes on beer. Let's take a closer look at this state here in the southeast of the graph. This state increased its beer tax and simultaneously saw a decrease in the fatality rate. So this decrease in the fatality rate cannot be driven by the state fixed effect, because the state fixed effect is time invariant, so it cannot drive changes over time. Overall, what we are seeing is a negative relationship between the tax change and the change in the fatality rate. That means that the average state that increased its tax saw a decreased fatality rate, and the average state that decreased the tax saw an increase in the fatality rate. Compared to our previous analysis where we only used data from 1982, we have removed the state fixed effect as a confounding variable. And therefore this negative slope coefficient that we see here probably has a better claim to measuring a causal effect than did the positive coefficient that we estimated before. Still, we understand that we have to be careful and that even the first difference method can lead to misleading results. This will be the case if tax changes are systematically connected to other changes over time that may impact the fatality rate. As an example, suppose that whenever lawmakers propose legislation that increases the beer tax, they are also adding legislation to have more traffic stops to increase road safety. So if that were the case, then this downward sloping line would measure the causal effect of the increasing the beer tax and simultaneously having more traffic stops. Now to proceed, suppose that we assume that the heterogeneity assumption for first difference estimation is satisfied. So this here gives us the desired causal effect. Let's also estimate standard errors. So now here we see our exact numerical value for our point estimate. We have a standard error, we have a t-statistic, we see this is significant at conventional confidence levels, and we get also a confidence interval for the size of the causal effect.